Hello, my name is Henrik Plate, and I'm a security researcher working with Endo Labs to secure the way developers and development organizations consume open source. And the way we want to do this is by considering and analyzing the program code of those open source components, all the single functions and methods getting executed, and not by looking at metadata that people attach to coarse-grained projects or packages, and which often leads to drowning developers in false positives. At Endo Labs, in a nutshell, we use such program analysis techniques to support open source risk and vulnerability management and to increase developer productivity. But I'm not going to talk about our own solution. You will need to look this up yourself, but about the general problem, the promises of program analysis, and one open source solution called EclipseSteady that I've been developing with fellow researchers over the course of several years. This is how the agenda looks like. I will start with a quick motivation for program analysis. I will explain how EclipseSteady works. I will demo the solution, and then I will finish with a couple of takeaways and limitations. So we all know the software industry depends on open source. Open source is just everywhere. 80% of typical application code bases come from open source projects. In other words, 20%, sometimes less, are specifically developed for a given application. For example, the business logic or some glue code. We speak of dozens to hundreds of dependencies, only a few of them being handpicked consciously by developers, but the majority of them being transitive dependencies, automatically pulled into a development project. And this is not even considering all the open source code that we download and execute in our CI/CD pipelines on developer workstations and all the lower parts of the software stack. Another way to look at this is to not count components or dependencies, but count all the individuals who dedicate their time to develop those solutions. This is a screenshot I took 2 or 3 years back, showing that there are 10 direct contributors to EclipseSteady developing its functionality, compared to more than 23,000 indirect contributors, people that contribute code to any of the open source components that EclipseSteady is built upon. And this is really amazing. It shows the beauty of this whole open source ecosystem and model. But this heavy dependency on open source also comes with security risks. One being the use of components that have known vulnerabilities and which can be exploited in production environments by attackers. For example, to create denial of service attacks or to exfiltrate information from those systems and applications. The first time I came across this, or which made the problem really apparent back then, was a paper called The Unfortunate Reality of Insecure Libraries back in 2012. And the authors found that in average, a Java application comprises 30 open source libraries, typically at least one with a known vulnerability. And those 30 open source libraries represent up to 80% of the code base. So this is the first time, the first occurrence of this 80% that you read every now and then on different blog posts and vendor reports. They came up with a second version of that report in 2014, where they found that the download number of Java components from Maven Central doubled from 6 billion to 13 billion between 2012 and 2014. And those numbers, of course, only ever increased since then. In 2013, the Open Web Application Security Project included the use of components with known vulnerabilities in their top 10 security risks for web applications. And in 2021, that has been promoted from the 9th to the 6th place and slightly renamed to also include the problem of using outdated components. The prevalence has been and is still widespread. Everybody's using open source. But the detectability got better over time with open source solutions and commercial vendors becoming active in this area. A study from 2017 found that 12 out of the top 50 data breaches in 2016 were due to the use of components with known vulnerabilities, including the Panama Papers breach. And all that was before Equifax happened and before Log4Shell. So by now, developers really entered this treadmill of activities they need to carry out over and over again. They need to detect whether any of their components is subject to a known vulnerability. They typically use certain tools which come with false positives and false negatives. So they need to figure out and do the triaging. And for all the false positives, so there is indeed a known vulnerability in one of their components, they need to understand whether this vulnerable piece of code is really relevant in their specific application context. Can it be executed? Can it be exploited by attackers to take advantage of the vulnerability? If yes, if the conclusion of that assessment is positive, the developer has to mitigate the problem, which could be very easy, maybe just updating a minor version or a patch version, or it can be more complex in case the application is on a relatively old release and the migration path is not straightforward, or it's an unmaintained vulnerability, unmaintained project, and there is no patch available at all, and so forth and so on. Once a patch is produced, that application patch has to be given and delivered to the customers, which again can be very easy. In case of cloud applications, you just deploy once and the fix becomes available and rolled out to just everybody. Or more complex in case of on-premise applications, where an application patch has to be given to all the customers who need to test it before releasing and deploying this in their respective production environment, which could be a lot of effort on the shoulders of these these customers. This slide explains why vulnerability assessment or impact assessment is so difficult. You see on the right-hand side the dependency graph of the Graph Maven plugin. The plugin itself is the gray box on the very top. It has 8 direct dependencies and 34 transitive dependencies. The depth of the dependency tree is 7. And so you see really the majority of the dependencies of this plugin is transitive. And so it is not necessarily known or understood by the application developer why a certain dependency is existing in this dependency graph. Why should he? It's kind of considered internals of the direct dependency that he chose at some point in time. Still, interestingly, the majority of the vulnerabilities are found in the transitive dependencies. And moreover, interestingly, not all of the code of those dependencies is used. Sometimes only certain functions and features of a dependency is used, and sometimes, even though it is pulled into the project, no single line of code is ever executed or could be executed in the context of an application. It's just load ending up in the dependency graph of an application. So maybe you wonder why bothering with such complicated assessment? Why not just simply update such vulnerability dependencies to a fixed release? Well, this depends on the lifecycle phase your application is in and the deployment model. The earlier you are in your application lifecycle, the easier it is to just, do this other update and resolve potential problems as part of the development effort. Anyhow, it is maybe not released and shipped and used anywhere. And it is much more difficult and more costly and more important to understand in later lifecycle phases. So again, suppose you have your application already shipped to customers. Just updating would mean you create a new application patch that has to be provided to, tested by, and installed by all those customers. Again, it's quite some effort, and you will only want them to do this for vulnerabilities that really matter. So you wouldn't want to always update by default, causing all this effort for those guys. And of course, updates can also bring in breaking changes and semantic changes that basically, which could fail the compilation of your application or change the logic. This slide is another example why it is difficult for developers to use security, the little information part of security advisories to perform such impact assessments. So here you see a vulnerability in a component called Eclipse Mojara, published in 2018. And what you see on the screen is really the whole thing, the whole content of that CVE. A short description, 2 sentences, a severity rating following CBSS, references, as well as an enumeration of affected products. And here, CVEs rely on CPEs, which are so-called Common Platform Enumeration Identifiers. They denote vendors and products and versions affected by the respective vulnerability. In this case, Eclipse Mojara up to excluding version 2.3.5. So why is it difficult for developers to use this information for context-specific assessment? First, the description is very short and concise. So if Eclipse Mojara is a transitive dependency, how could an application developer ever know whether the method getLocalPrefix in the class resource manager matters in his application context? That is very detailed information of no immediate use, I would say, for the application developer. And also those references, in this case, to the fix commit and to the Jira issue are not always much of a help and provide rather unstructured or little additional information supporting developers. Secondly, those CPE identifiers I've been mentioning, they do not really correspond to the Maven artifact identifiers. So here we have 2 different languages. The CPE identifiers talking about Eclipse Mojara, but if you search for Eclipse Mojara on Maven Central, you will find 36 search hits, but none of them is the actual artifact that contains the vulnerable code, which is org glassfish javax faces. And so this demonstrates the problem of mapping names given by people to each other in the hope to find the right match. Another problem is not all ecosystems are well covered by NVD. Java is relatively well covered. NPM, for example, is not so well covered. And yet another problem is that those descriptions are error prone. So when we looked at this vulnerability back in 2018, we looked at the source code, the fix commit in Eclipse Mojara's Git repository, and the bytecode. And we found that the versions 2.3.5 and 2.3.6 still contain the vulnerable code. So we reported this to NVD, and they were then updating the description. So there are, on high level, 2 different approaches to support developers in detecting dependencies with a known vulnerabilities. The first is based on metadata, so data about code, primarily based on package names, package versions, CPE identifiers, or digests, which are which are mapped against each other to understand whether there is a vulnerable dependency, a vulnerable component in a given dependency tree of an application. A good example for this is OWASP dependency check, a nice lightweight solution they've been developing for a couple of years now. It can be easily run from the command line without any really installation efforts. It will download the entire NVD and try to map CVEs against the dependencies of a given project. The other approach is based on code, avoiding as far as possible, the use of any metadata. What you see on the right-hand side is a method that was introduced by developers to fix a given vulnerability, CVE 2022 something. And so when looking at code, the presence or absence of this method would already give you some clues and indicators on whether you use a vulnerable version or a fixed version of the respective component without needing to look into package names and package versions and to do this mapping. One example for a code-centric approach, for a tool implementing this approach, is Eclipse Steady. It is relatively heavyweight compared to OWASP dependency check on the one side, because you need to run a Docker Compose application on a workstation or better in some internal cloud. But secondly, because it requires fixed commits. Fixed commits, again, being the changes done by the open source developers to overcome a problem. And those fixed commits are not systematically collected by public vulnerability databases. And so coming up with them is a little bit of a manual effort, which makes it more involved to use open source code, this open source code-centric solution. But once you have it, you can do additional analysis beyond the capabilities of metadata-based approaches, which do not know much about the code. One example being this impact assessment reachability analysis. What you see here on the right-hand side is the result of a call graph analysis, a call graph that was built starting from the application methods here in green. And in this call graph, there was also a path from those application methods to one of the vulnerable methods of this component. In this case, a class constructor called interpolator string lookup. And so the presence of this path shows the developer that this vulnerable code is potentially executable in the context of his application. And also, this information can be used to maybe implement custom controls. So you could pick maybe the most suitable method to implement a custom sanitization or an authorization check if ever the update is not possible. And other possibilities include the support of developers in choosing the best update path or migration update path, because you can understand whether methods that you call, APIs in a dependency that you call, are also present in the newer releases, or maybe not. And if not, they would result, because if not, they would result in compilation exceptions. So I hope this gives you an idea of the possibilities and opportunities of using code-centric analysis for vulnerability management, vulnerability assessment. Coming back to this treadmill mentioned before. So metadata-centric approaches, due to the unawareness of code, can only support in the initial detection, while code-centric approaches can also help at other later activities, reachability, impact assessment, and mitigation. But not only that, they can also identify and remove bloat, which is a very interesting feature. Coming back to what I was mentioning earlier on, only fractions of those open source dependencies are actually used in a given application context. Sometimes entire dependencies are pulled automatically, but not touched, not used at all. And of course, you could remove those dependencies, and this will improve several aspects of your application. The whole application will become a little bit smaller, slimmer, build times may become better. And for those that you remove, there will be no new known vulnerabilities popping up the next time you run your open source vulnerability scanner. So this is really, this bloat removal and bloat identification is one of the very promising features supported by program analysis. So next I mention how Eclipse Steady approaches the whole problem and how this implementation looks like. So when performing the assessment, what you really want to know is a given vulnerability exploitable in my specific application? If yes, fix it now. If no, fix it later. Reduce the priority. Look at the things that matter more. But this is a very difficult question to answer because exploitability really depends on so many aspects. Could be configurations, sanitizations in place, depending on how the application is deployed, depending on the architecture. And so we decided to address and answer easier questions. And so rather than judging exploitability, we like to answer with Eclipse Steady two questions. First, is vulnerable code contained? And if vulnerable code is contained, then is that executable in the context of an application? And so this is based on the assumption that if an application executes code for which a security fix exists, then there is also a significant risk that the vulnerability can be exploited. It must not be exploitable, but there is a risk it is exploitable in this specific application context. To answer whether vulnerable code is contained, we will have a look at, or we look at fix commits. And to answer whether vulnerable code is executable, Eclipse Steady uses a combination of static and dynamic analysis. And if it is found executed, for example, as part of JUnit tests, or if it is potentially reachable according to call graph analysis, then we say the vulnerability is, there is high risk, you better do something about it. If not, there is low risk. So how do we answer those questions? For the first one, is vulnerable code contained? We start from an advisory, could be a CVE, could be any other disclosure on Twitter, whatever. What is important is to have the patch information, the fix commit, fixing the problem, which is our starting point. And getting there, this is why I put a question mark, is not straightforward. It would be nice if public vulnerability databases collected this information on a systematic basis, but they do not, unfortunately. But once we have the fix commit, we can basically look at every commit and the changes introduced by them to understand which are the methods and constructors added, deleted, and modified. And that is what we call a change list. You will see one such change list later on. This is a screenshot from the UI, and here you see some elements of a change list of the vulnerability in Apache Commons text. So here, the fix commit was B9B something in the Git repository on github.com. And they were modifying an enumeration, deleting a method, modifying a constructor, and so forth. Here's the interpolator string lookup you were seeing earlier on in the call path. And this change list is then input to answering the second question, which is that vulnerable code executable or not? What you see here on the screen is basically one application with one method, number 4, part of the set of application methods. This application has a direct library dependency with methods 5 and 6, and it also has a framework dependency with methods 2 and 3. The library dependency also brings in 2 transitive dependencies with methods 7 and 8 respectively. Those methods call each other according to those edges and arrows. The red ones are dynamic invocations. Could be reflection, could be, as in the case of frameworks like Spring Boot, invocations happening by classes generated at runtime. And so those dynamic invocations typically represent a problem for static source code analysis tools. So how would we use Eclipse Steady to understand whether the vulnerable methods 2 and 8 are relevant, are reachable in the context of this example application? We do this by running several analyses one after the other. We would start with a reachability analysis, a call graph analysis starting from the application method number 4, and we would try to see what are the other methods that can be reached starting from 4, which in this example are 5 and 6, and we stop there because the call graph construction fails to understand the dynamic information, the dynamic invocation from 6 to 7. And also, since we used 4 as an entry point, as a starting point of the analysis, we also do not find this dynamic invocation of the framework method 3 of the application method number 4. As a next step, we run a dynamic analysis. What we do is we instrument all those methods of the application and all of the dependencies, and every time we find that such a method is executed either as part of a JUnit test or as part of really a runtime integration test, or maybe an application deployed in a runtime environment, we trace this information, we write it down. And in this example, the dynamic test found that the framework method 3 and the method 7 part of the transitive dependency was also executed. And in the next step, we can run again a static analysis, but this time we do not take the application methods as a starting point to construct the call graph, but we take the traced methods 3 and 7 as a starting point. And so this basically allowed us to bridge these dynamic invocations, to get beyond those dynamic invocations. And starting from 3 and 7 respectively, we find that the vulnerable methods 2 in the framework and 8 in this rightmost transitive dependencies are potentially reachable. You can read all the details in the research paper here, put on the slide, including an empiric study for how many vulnerabilities were reachable in the respective, after the respective analysis steps. And we found that, if I remember well, something around 10% of vulnerable code was only reachable due to this combination of static, dynamic, and static analysis. So how does it look like in practice? For this, I would like to use again this Apache Commons text vulnerability I've been mentioning earlier on. It has been disclosed in October 2022. Apache Commons text offers different features related to strings, texts, not very surprisingly. For example, computing the Levenstein distance or the Jacquard distance and so forth. But it also offers what they call a string substitution, where you can include variables in strings that will be replaced at runtime. In the first box, the Java version and the operating system name will be replaced by the actual values by the method replace system properties. The vulnerability that was discovered is basically about certain dangerous interpolators or substitutors being included by default and enabled by default, one of them being for JavaScript. And so in the versions prior to 1.10.0, this would have allowed for remote code execution if a user-controlled, attacker-controlled input contains a JavaScript variable that is replaced by the library. In this example, shown in the second box, the malicious script that would be executed as part of this replacement, as part of this substitution, would be java-lang runtime, get runtime exec, and then in order to operate an operating system, execute an operating system command, in this case, it would just touch and create a certain file. Thing about Apache Commons text and this vulnerability is that users are only affected if they directly or any of their dependencies make use of this string substitution. They certainly know for their own code, but how could they know for all of the direct and especially all the transitive dependencies? And to figure this out, we will have a look at Eclipse Steady. So this is how the application, a very simple sample application looks like. It has two dependencies, Apache Commons text in a vulnerable version and JUnit. The only class, the main class, has a print method in which such a dangerous string substitution takes place. This is really copy and paste from the original advisory coming from the GitHub security team. And so here, if the replace method is called on this interpolator, this runtime exec statement would be executed, and there will be a file foo being created. So I can quickly demonstrate this. First, I will remove the file that is existing. And then I can just run the test, because there's one test case which is invoking this print method. So once I do this, you will see this foo file popping up again on the left-hand side. There it is. Now, in order to analyze this application with Eclipse Steady, we will do the following. I already included the a profile pointing to or referencing Steady's Maven plugin. So I can invoke the goals of this Steady plugin very easily. And so here, first of all, I would clean the target folder locally on my disk, but I would also clean the analysis results that already exist in Steady's backend, because I ran some analysis early on. So let me just clean all this. Once that is done, I can basically create a method level bill of material using the app analysis goal. What happens if I run this? Basically, the Steady Maven plugin looks into each and every method of the application and each and every method of all the dependencies to see whether there is any vulnerable code contained. And this is how it looks on the front end. So here we have the demo comments text vulnerability. Here we have all the dependencies, the two direct ones you have seen earlier on in the POM file, as well as two transitive ones brought in by, I think, one by JUnit, the other one by comments text, probably. And we also see that comments text has been found to contain vulnerable code. And this decision hasn't been made on the basis of the name of this archive or the coordinates of this archive, but it has been taken on the basis of the presence of vulnerable methods and constructors. And so here you see this kind of the same information I've shown you earlier on the slide. So these are all methods added, deleted, removed as part of the fix commit, which is this one, by the open source developers. And for each construct, for each method and so forth, we check whether it is contained in this respective archive. So the archive could be really named completely different. We would still be able to find the signature of those methods, constructors, and so forth. Now, we just found that vulnerable code is present. We do not know yet whether it's reachable or not. To do this, we can just run another goal, and which is called A to C. So this is the call graph construction starting from the application A to C, the change list of modified open source methods. If I do this, there will be a call graph constructed, and it will be checked whether the vulnerable methods are part of this call graph and how this path is looking like from the application method to the vulnerable method. So if I reload this, toggle the advanced analysis, there's now this red paw popping up indicating that some of the methods have been found reachable according to the call graph analysis. And all those methods found reachable have this red paw and this detailed table. If I click on it, there is this call path you have been seeing earlier on. Again, main is a method from the application, and by calling different other methods of different other artifacts, or potentially different artifacts, in this case it's always commons text 1.9, you end up in one of the vulnerable methods, in one of the methods the developers had to change to fix the problem, right? Now that was the static analysis, but I've explained earlier on, there are deficiencies, problems that make static analysis fail, reflection, dynamic programming techniques. And so we could also run additionally a dynamic test where we instrument all the code. This is done using yet another Maven goal. Here in this case, it's a little bit more involved. I basically have to prepare an agent comparable to the agents of Jacaco or other coverage tools. I run the JUnit tests, and then I upload all the information that is saved locally. Also, I say how much information I would like to collect during the instrumentation. So in this case, I would like to find all touch points, which are API invocations from the application to the library. And I would also like to have the complete stack traces showing me the entire path. So I run this. Tests are executed. Foo would have been created yet another time if I deleted it, and then everything is uploaded. And the front end, let me reload this once more. Now the red paw on the very rightmost column also appears. You see here that some of those methods are both statically and dynamically found reachable. Here, hovering over it, you see the the execution time. And if you go into the call graph, into the call path, you will see that there is this reddish overlay over the black edges that existed before, indicating the dynamic execution. So here we start from a test method, test print, which invokes the print method you have seen earlier on in Visual Studio Code, which again takes this path all the way to one of the vulnerable constructs in Apache Commons text. Right, this being the different analysis goals, giving the developer a feeling for whether the vulnerable code matters in his application context. Now, let me quickly go to other features of Eclipse Steady that I mentioned earlier on. So next step would be to mitigate. And here we see basically the number of vulnerabilities per component and the latest release published, which would be alternative to fix the problem. If I go on this, I will see first of all those touch points in the first table, and sorry for all this wealth of information that is always very developer oriented. The first table contains those touch points. So this is where our application calls into a library. So here there are 3 of these calls into a static initializer, into the replace method. You have seen this earlier on, and the create interpolator. Those touch points have been found both in the call graph and were actually traced during JUnit test execution. This is not always the case. Sometimes you have trues on in one column and false in another column, showing how the different techniques complement each other. And then further below, you have basically the available non-vulnerable releases to which the developer could upgrade. And we see that for all these different touch points, we check, are those that I call also available in the non-vulnerable release, in the fixed release? Because if not, I would have a compile issue. And we also show what we call the body stability, trying to indicate how different is the fixed version from the version that I use. And so in this example, when going from 1.9 to 1.10.0, 170 out of the 171 methods that were part of the call graph have the same method body. So there was very little change from one version to the other, and so the likelihood of regression is relatively low. And in other examples, you would see that if there are multiple fixed releases available, you would see how this reachable body stability decreases the greater the distance gets between what you use and this non-vulnerable fixed version. And last but not least, I would like to quickly show this table. This is a first attempt to understand what are bloated dependencies. I mean, here we have 4, so there's not so much, likely no bloat at all, but the table gives you an idea of how this can work out. So here you see 2 compile time dependencies. Test dependencies were excluded. They have a total of 3,671 and 1,149 methods and constructors, out of which, according to the JUnit tests, to the dynamic tests, 10 and 130 respectively were actually executed, and 6 and 142 were potentially executed. They were part of the call graph that we have built. And so removing this would likely cause some troubles. But in other cases, in bigger dependencies, whenever there is no single method potentially reachable or actually executed during the tests, it would be worthwhile to removing this dependency and seeing whether the application still works. This is concluding the demonstration. So let me get back to the slide deck. So to conclude, I hope you have seen the capabilities and possibilities of supporting vulnerability management with code-centric program analysis techniques. They can reduce false positives and false negatives. So compared to all these metadata-centric approaches trying to map names against each other, but also false negatives because they can cover this phenomenon of rebundling, where classes from one project are rebundled, copied into Java archives or other projects, which would not be found on the basis of mapping names against each other. You can prioritize findings because of having this application context, understanding code reachability, and they can help you they can help you with updates, avoiding regressions, and to identify software bloat. On the negative side, I have to mention that, of course, they struggle with so-called configuration vulnerability. So if a fix consisted only of changing a default configuration in a properties file or XML file that is coming with a Java archive, code-centric analysis cannot do much. And secondly, reachability and reachable is not the same as exploitable. There is a certain class of vulnerabilities, namely deserialization vulnerabilities, especially those using the the old Java way of serializing Java objects, where for a vulnerability to be exploitable, it is sufficient to have a vulnerable class, a gadget class in the class path. So in this special case, it doesn't matter at all whether this vulnerable class is in a call graph computed on the normal expected behavior of an application. It's just sufficient to be hidden somewhere in the class path to be exploited by attackers that send deserialized objects of that class to an application in order to trigger the vulnerability. The particular limitations of Eclipse Steady are as follows. First, as I've mentioned earlier on, none of the existing public vulnerability databases references fixed commit in a systematic fashion. This is why the tool has a limited coverage. So right now there are 700 vulnerabilities in a dedicated open source project called Project KB, where we listed the fixed commits for those 700 vulnerabilities. So they are the input for the analysis you have seen earlier on. Secondly, we only support, or Eclipse Steady only supports Java. Python, limited Python support is available, but that is rather beta and does not include all the reachability analysis. And last but not least, compared to other approaches, it is relatively heavyweight in the sense that you need to have a Docker Compose application running ideally in a private cloud. All right, this concludes my talk. I hope it was interesting and I convinced you of, the potential of using program analysis techniques. Thank you so much.